Hello guys, in this video we are going to be looking at the study of numerical sequences and we are going to be solving a tutorial problem. So the question reads, we consider the sequence xn and yn defined by integrals. Xn is the integral from 0 to 1 of t to the n cos t with respect to t, and yn is the integral from 0 to 1 of t to the n sin t with respect to t. Question 1a, show that xn is of positive terms. Question 1b, study the variations of the sequence xn. Question 1c, what can be deduced about the convergence of the sequence xn? Question 2a, show that for any non-zero integer n, xn is always less than or equal to 1 over n plus 1. Question 2b, deduce the limit of the sequence xn. Question 3a, with the help of integration by parts, show that for any non-zero integer n, x of n plus 1 is negative into n plus 1 times y of n plus sine 1, and y of n plus 1 is n plus 1 times x of n minus cos 1. Question 3b, deduce the limit of the sequence yn. Question 4, determine the limit as n tends to infinity of n times xn, and also the limit as n tends to infinity of n times yn. Okay, so we are going to begin with the first question, which is asking us to show that xn is of positive terms. So we have been told that xn is the integral from 0 to 1 of t to the n cos t dt. It means that the variable t is in the interval 0 to 1. So from there we can raise all the sides to the power n, and the exponential in a positive interval is an increasing function, so the inequality signs remain the same. So we have 0 is less than or equal to t to the n less than or equal to 1. We can now multiply all through by cos t, and we clearly know that in the interval 0 to 1 the cosine of t is above the x-axis, so it is positive, so the inequality signs still remain unchanged. We can now integrate all through, and then we clearly see that our 0 will be less than xn and will be less than sine 1. And from here we can conclude that xn is of positive terms because it is between two positive numbers, since the sign of 1 is positive, it's above the x-axis. So xn being between 0 and sine 1 means that xn is of positive terms. Nevertheless, we could still show that the function t to the n cos t is a positive function, therefore its integral in the interval 0 to 1 will also be positive. So we just concentrate on the this part of the inequality and we prove. But nevertheless, showing what I have shown, or showing that t to the n cos t is a positive function and integrating all through, we still get the same results. So we have succeeded in proving that x of n is of positive terms. Now question b is asking us to study the variations of the sequence x of n. So all we need to do is to get the difference between x of n plus 1 and x of n. So x of n plus 1 minus x of n, to get x of n plus 1, I just need to come to n and replace the n with n plus 1. So x of n plus 1 minus x of n will result to this integral. When you subtract the two integrals, you're going to see that since you're integrating with same bounds, you can just bring the integrals together and you factorize t to the n cos t. If I multiply all through by t to the n cos t with the first term, I'm going to get t to the n plus 1 cos t, and minus with the second term t to the n cos t, and the integral sign is going to distribute over the subtraction, so we still have the same results. So now we know that t is also between 0 and 1. It therefore means that t minus 1 will be less than 0, okay, if you consider the upper part of the integral. So it means that the function here t minus 1 is negative. Now t to the n cos t is positive, so when we multiply a positive function and a negative function, we get a negative function, and integrating from 0 to 1 of a negative function, we get a negative value. So at the end of the day, we can conclude that xn plus 1 minus xn is always negative, which means that the sequence xn is decreasing. Right. The next part says what can be deduced about the convergence of the sequence xn. Now it should be seen that from the first question we have proven that xn is actually bounded. From the second question we have seen that xn is monotonic. So these two conditions clearly tells us that the sequence xn is convergent. So every monotonic and bounded sequence is convergent. Alright, so for those of you who have not subscribed to the channel, endeavor to subscribe, like, share, comment on the videos. Thank you very much. Question 2a, show that for any non-zero integer n, x of n is less than or equal to 1 divided by n plus 1. Alright, so we see begin with our basics, which says 0, t is between 0 and 1. From there, I'm going to take the cosine on all the sides, and since the cosine function is a decreasing function in the interval 0 to 1, then my bounds are going to switch. So rather, I'm going to have cos 1 less than or equal to cos t less than or equal to cos 0. But cos 1 is cos 1, cos t is cos t, and cos 0 is 1. I can now multiply all through by the function t to the n, and since it is a positive function, my inequality sign remains unchanged. I can now integrate with respect to t from 0 to 1 all through, and from there we clearly see that the middle term is x of n. If you integrate cos 1 is a constant. If you integrate t to the n, we get t to the n plus 1 divided by n plus 1. When we fit our bounds, we just get cos 1 over n plus 1. The same thing here, integrate t to the n, we get t to the n plus 1 over n plus 1. If we fit our bounds and subtract, we get 1 divided by n plus 1. So it means that our x of n is actually less than 1 divided by n plus 1, which is what we are required to prove. Alright, now we have to deduce the limit of the sequence x of n. Now we have seen that x of n was positive and it is less than 1 over n plus 1, so it means that it is between 0 and 1 over n plus 1. Now the limit of the lower bound is 0 and the limit of the upper bound is also 0. So by the sandwich theorem, the limit of x of n is equal to 0 because x of n is bounded by these two sequences and both sequences converge to the same value. So x of n is, the limit of x of n is 0. It can also be seen that the sequence x of n was monotonic decreasing and bounded from below by 0, so it converges to its lower bound, which is 0. Thank you guys for watching, and see you in the next video. Alright, hey, sorry, I actually thought the video is finished. That's really funny. Anyways, question 3a, with the help of integration by parts, show that for any non-zero integer n, x of n plus 1 is negative into n plus 1 times y of n plus sine 1, and y of n plus 1 is n plus 1 times x of n minus cos 1. Alright, so we are going to begin with x of n being equal to the integral from 0 to 1 of t to the n times cos t dt. So to use integration by parts, we are going to let a function to be u and another function to be dv. So we can take our u to be cos t. When we differentiate, we get our du to be negative sine t. We take our dv to be t to the n dt, and then we get our v to be t to the n plus 1 over n plus 1 after integrating dv. Now integration by part formula says our x of n will be uv minus the integral of v du. Our u is cos t and our v is this quantity from 0 to 1, then minus the integral of v du. Our du has a negative sign, so it cancels. It becomes, we multiply the negative sign with the negative sign in the formula, it becomes positive. We factorize the 1 over n plus 1 in v, and then our du is sine t. So we now multiply t to the n plus 1 with the sine t, and we get this. Now from there we can clearly see that if we fit the upper bound, we are going to, and the lower bound, and subtract here, we get cos 1 on n plus 1. Here we just get 1 over n plus 1, but this integral here is y of n plus 1, because y of n is the integral from 0 to 1 of t to the n sine t. So y of n plus 1 becomes integral from 0 to 1 of t to the n plus 1 sine t. So from here we can multiply all through by n plus 1, and then we look for y of n plus 1. So y of n plus 1 becomes n plus 1 n plus 1 times x of n minus cos 1, which is the second proof. Now for the first proof, we now consider the integral y of n to be the integral from 0 to 1 of t to the n times sine t dt. So we still use integration by parts by letting u to be sine t, differentiating and letting dv to be t to the n dt, and integrating. Now the formula says we need to take uv minus the integral of v du. If we do that correctly and simplify, we are going to arrive at x of n plus 1 to be negative into n plus 1 times y of n plus sine 1. So we have succeeded in proving the first and the second proof.